Let's go through making a sketch of a polynomial, also finding the function for a polynomial given the graph, and then a little application at the end there. All right, this first one, we have a function x plus 3 times x minus 2 squared times x plus 1 cubed. So, with this, there's a few ways we can start. Let's start with the long run behavior. So for long run behavior, what I want to do is evaluate what is our leading term. Now the form that's given to us here is the factored form, so it's a little more difficult to see what our leading term is. But there's a little shortcut, because you might be inclined to start multiplying all of that out, which is fine, but it's a lot more work than we need to do. The leading term is going to come through from basically multiplying x with itself whenever we can. So what I'm going to do is, from this form, so I have x plus 3, I'm going to grab that value of x. So I'm going to build my leading term, so I'm going to grab x from x plus 3, and then I'm going to multiply it with, so I have this x minus 2 squared. What I'm going to grab from that is that x right there and that exponent of 2. So my leading term, I'm going to have x from that first piece and then times x squared. And then I'm going to go times, and that last one, x plus 1 cubed, I'm going to grab that x cubed. So really it's going through and grabbing anything with x and the exponent that's attached to it. So I end up for my leading term with x times x squared times x cubed, which is x to the 6th. And that would be my leading term. If there was a number attached to any of these, I'm just going to make a side note of like, what if this was x minus 1 times negative 2x minus 2 squared times x plus 1 cubed? If I wanted to make the leading term for that scenario, I would have x, and then where I changed it to a negative 2x squared, what I would do is put negative 2x in parentheses and square it. And then I'd have times x cubed right there. So what this would turn into is negative 2 squared would be a positive 4. Then I have x times x squared times x cubed, so x to the 6th. So if there are numbers attached, you keep them attached to x, and then if there's an exponent, they go under that exponent as well. All right, that's just a side example there. So if our leading term is x to the 6th, so this is an even power, so in terms of long run behavior, this is going to behave like a parabola, and because my leading coefficient is positive, it's going to be opening upward. So what I do on the graph is I just make a little note to myself, like on the left-hand side of the graph, we're going up and off to positive infinity. On the right-hand side of the graph, we're going up and off to positive infinity. So I just have these two arrows pointing upwards on the left-hand side and right-hand side of the graph, because that's what should happen in the long run of our graph. All right. Next, we're going to fill in the blanks for the short run behavior. So let's start with the vertical intercept, just because that tends to be pretty quick to find because it's just a matter of plugging in x equals 0. So we have 0 plus 3 times 0 minus 2 squared times 0 plus 1 cubed. So 0 plus 3 is 3 times a negative 2 squared is positive 4 times 1 cubed is 1, so that's 12. So we're getting 0, 12 as a coordinate here, which is actually up and off of our graph here, so my grid's too small to show that coordinate. Sorry, I want to see that coordinate, so what I'm going to do is I'm going to adjust my scale here. So I'm going to have it go for the y-axis 2, 4, 6, 8, 10, 12, 14, 16. Okay. Sorry, just adjusting that because I do want to see the point. Okay, so 0, 12, We have a coordinate right there. Now let's take a look at our horizontal intercepts. So from the factored form, what I can do is just grab the zeros. If you want to solve for them, that's fine. But basically, because I have these three factors showing up here, I'm going to have 3 zeros. So from x plus 3, I'm getting an x equals -3. So that's giving me a coordinate -3, 0. And what I could note is that the multiplicity is 1. Then from x minus 2 squared, so that x minus 2 is going to give me x equals +2. So that's giving me 2, 0. And then that exponent of 2 is giving me a multiplicity of 2. So with that one, there's going to be a bounce when we get to that part of the graph. And then x plus 1 cubed, so that x plus 1 means that we'll have x equals -1. So we're getting a coordinate -1, 0. And this has a multiplicity of 3, which means we're going to flatten across that point there. Okay, so I'm going to graph these 3 coordinates. We have -3, 0, we have +2, 0, and we have -1, 0. So what I'm going to do is kind of follow how my graph should go. So let's see. At -3, 0, we just go straight through. So we're going to come from positive infinity. We're going to go straight through that -3, 0. We're going to need to turn somewhere. I don't know exactly where. And that part, that kind of idea is where we're actually not graphing the function, we're sketching the function. So we're just going to say we go down, we turn, and as we come up to -1, 0, so we need to flatten across it. So what I'm going to do is flatten, and I know I need to go up and touch 0, 12, and then we're going to turn at some point, go down, and we're going to bounce off of 2, 0, and that works perfectly because then we'll be going up and off to positive infinity again. All right, so let's make this graph. I'm going to come down from positive infinity, go straight through -3, 0, turn, flatten across -1, 0, go up to 0, 12, turn, yeah, good enough, turn, come down to +2, 0, bounce, and go up off to positive infinity. It's a little silly, but it's just a sketch, and we hit the key points that we wanted to. Let's take a look at the graph in Desmos. Oops, there we go. All right, so this was x plus 3, x minus 2 squared, and x plus 1 cubed. All right, so I'm going to zoom out a little bit. All right, so we come down from positive infinity. We go through -3, 0, straight through. Or actually, our turning point is like way down at -35. But we didn't hit that, but that's totally okay. We turn, come up, and then this is where we flatten across -1, 0. So we're coming up to our x-axis, and then we just kind of turn to flatten a bit, and then turn to go up. So we're above the x-axis, going up through 12, 0. Then we're going to have this turning point, which is at like positive 32-ish. And then we turn, come back down, and when we reach 2, 0, it looks like a parabola in this section because we come down, turn at 2, 0 to go back up and off to positive infinity. All right, so that's how we can make a sketch. Pretty much those 3 pieces. We want the long run behavior to give us an idea of how infinity is coming into play. And then the vertical intercept will give us a coordinate. And then evaluating the horizontal intercepts with those zeros and their multiplicities will get us good short run behavior for our graph. So now let's go in reverse. let's take a look at this function here, and what we're going to do is come up with a polynomial that will work for it. Now, with coming up with the polynomial for this, I'm going to focus on creating the factored form of this polynomial. So, some things I want to notice. So we're starting at positive infinity and going off to negative infinity. So what that tells me is that in terms of degree, this is going to be an odd degree. So I'm just going to make some notes to myself. And also, in terms of starting at positive infinity and going off to negative infinity, where we have our leading coefficient, that leading coefficient is going to be negative. So I'm just kind of making notes to myself there in terms of long-run behavior. Leading coefficient is negative. All right, then what we can do is let's look at the x-intercepts, or actually let's start with the y-intercept, which is actually also an x-intercept because we're at 0, 0. So we have the coordinate 0, 0. What I can also see is at 0, 0, there's a bounce there. So that right there, because there's a bounce, I'm going to make a note that that 0 should have a multiplicity of 2. Okay, let's grab the other x-intercept. So we have an x-intercept at negative 3, 0. And that also has a bounce, so that's also going to have a multiplicity of 2. And then our last horizontal intercept is at 3, 0. Yeah, positive 3, 0. And we're just passing straight through there, so that's going to have a multiplicity of 1. All right, so putting our polynomial together, I'm going to call this, well, let's just call it f of x. What I'm going to do is use the letter a as just some unknown number, some number for my leading coefficient. So I'm going to go a and then times, and then what I'm going to do is create these factors based on those zeros. So let's see, I have 3 zeros here. So with that, I should have 3 factors. So working in reverse, and let's kind of look at this last example. So like getting the coordinate negative 3, 0 came from having x equals negative 3, which really came from seeing x plus 3 in a factored form. So here, like where I have the coordinate 3, 0, which is coming from x equals 3, that means I have a factor of x minus 3. So it switches sign as it moves between this factored form and solving for that coordinate. And then this has a multiplicity of 1, where I have negative 3, 0, so that's coming from x equals negative 3, and that's going to look like an x plus 3 in factored form. And then that has a multiplicity of 2, so I'm going to put an exponent of 2 on the outside of the parentheses there. Now when you have the coordinate 0, 0, it actually just shows up as x multiplying on the outside. And then this has a multiplicity of 2, so really this is going to be x squared. So I end up with f of x equals a, we're just going to have some number there, times x squared times x plus 3 squared times x minus 3, which that x minus 3 technically has an exponent of 1. All right, so I want to actually find the number for a that works, and what I should expect is a negative number to come through there, because if I start thinking about my leading term, I have x squared times x, so I'm getting x to the 5th out, which is perfect for the idea that we should have an odd degree. But right now it's positive, which the leading coefficient's positive, which that behavior comes from negative infinity and goes up and off to positive infinity, which is the opposite of what we're seeing. So I still need to find this leading coefficient here. So what I want to do is plug in a coordinate that is not an intercept. I don't want to use an intercept. And what's showing up on this graph here is this defined coordinate 1, positive 2. So I want to use that, where our output is 2, I'm going to go equals a times, and then plug in 1 for x. So 1 squared times 1 plus 3 squared times 1 minus 3. So 2 equals a times 1. 1 plus 3 squared would be a 4 squared, so 16, times 1 minus 3, which is a negative 2. So this is 2 equals negative 32a. And then we'll divide both sides by negative 32. So a is equal to a negative 1/16. So my function is negative 1/16 x squared times x plus 3 squared times x minus 3. And then we could put that into Desmos to check our answer if we wanted to. All right, our last one here is a word problem. So we have an open top box, and we want to construct it by cutting out square corners of a 14 by 20 centimeter sheet of plastic, then folding up the sides. So what this looks like, if I draw a rectangle here, so here's our 14 by 20. And what we do is we cut out corners, and we're going to use squares in the corners. So we'll have the upper left, lower left, upper right, lower right. And what that lets us do is we have these sides that then fold up and connect to make an open top box. So what we want to do is find the size of squares that should be cut out to maximize the volume of the box. So what we're going to do is call the side of the square x, because we don't know what that is. And that's occurring all over the place. Oops, x, 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 x. Okay, so when we fold up this box, I'm just going to draw a little picture of the box when it's folded up. And it's going to be open on top. So what we need to talk about is, for volume, we need length times width times height. So the height of the box is coming from this one of the sides of the squares. So the height is actually going to be x. The width of the box, so we have this 14 centimeters, but we're cutting out 2 squares from that length there. So what's going to happen is we're going to have that total of 14 centimeters minus x minus x. So that's actually going to be 14 minus 2x. And then for the length of the box, we have these total 20 centimeters, but we're going to take out 2 squares. So we'll have this 20 centimeters minus x, which is 20 minus 2x. So for volume, our length is 20 minus 2x times the width, which is 14 minus 2x, times the height, which is x. And what we want to do is maximize this. So actually we can leave it just like this. What we're going to do is use technology to help us out. So finding minimums and maximums from polynomials, we're going to rely on Desmos to help us out. So what we're going to do is graph our function. So we have 20 minus 2x times 14 minus 2x times x. Okay, so as we look at this, and actually I'm going to adjust my axes a little bit so it's a little clearer. Let's see, I'm going to go 0 to 50 on the x-axis. Let's go -5 to +50 on the x-axis. And then for the y-axis, let's go -10 to, let's go to, let's see, how about 350? Yeah, that looks pretty good. Okay, so the graph, it's starting at 0, 0, it's going up, it turns at some peak right there, turns back down, goes below the x-axis, and then comes back up to go through off to positive infinity. So this is mapping the volume of the box. Something we need to think about is what makes sense for our domain here. What are some limitations that we have? And something we could think about is like focusing on this side length of 14 minus 2x. Basically, we don't want any negative numbers to come through here. So like if I plugged in 7 for x right there, so 14 minus 2 times 7, that's going to make that width of the box 0. And that doesn't make sense for us to evaluate that. And then you can imagine that I actually don't want to put anything larger than 7 in either. So what we get is this kind of restricted domain coming through just based on the setup of this problem. So really, I only want to look at x values that are between 0 and 7. So from that, looks like our graph has an x-intercept at 7, 0. So really, I don't want to use anything to the right of that. I just want to focus on what's in between 0, 0 and 7, 0. So what I'm going to do is there's this peak that's between those two that's happening at 2.704, and then the output is 339.013. That's the coordinate that I want to graph because that's creating a maximum. So let's write that coordinate down, a 2.704 and 339.013. So that's giving us a value for x, which is the side of the squares that we're going to cut out. And then that 339 is the volume of the box. So what we would want to do is use 2.704 by 2.704 centimeter squares to get a maximum volume of 339.013 centimeters cubed for volume.